Hello, welcome to video lectures. This topic is on cantilever. Myself, Karanam AJITH, Assistant Professor, Vijayanagara College, Hosapete. Now let us understand what is a cantilever. A beam clamped horizontally at one end and loaded with a weight at free end is called as cantilever, which is represented as shown in figure. Consider a section at the point P which is at a distance x from the fixed end, then neglecting the weight of the part between the point P and the free end, the moment of the external couple is given by force into distance, that is given by mg into distance is L minus x. The bending moment of the section at the point P is given by ya k square divided by r, where r is the radius of curvature of the neutral axis at the point P. At equilibrium position, mg into L minus x is equal to ya k square by r, or r is equal to ya k square divided by mg into L minus x. From this expression, we find that as x increases, r also increases, the maximum and minimum values being at the free and fixed ends respectively. Therefore, the radius of curvature of the neutral axis r varies from point to point of the cantilever x. Bending is said to be non-uniform. Then if P dash is another point on the bent cantilever at a small distance dx from P, then since P and P dash are very near, we can assume that the radius of curvature r is practically the same at the point O as its center of curvature. As the angle between the tangents of the points P and P dash is d theta, which is represented as shown in figure, that is, which forms an arc, that is between P dash is given by d theta. Therefore, the angle between the points P and P dash is d theta, that is, angle P dash is d theta, or dx is equal to, that is, the distance along the arc length P dash is dx, and the length, the radius which describes an angle theta, that is given by r into d theta, that is, in other words, linear displacement s is equal to r theta, as we said earlier. In the same way here, in place of s we have to replace by dx, and r theta is given by r into d theta, or r is equal to dx by d theta. Then substituting this value in the expression 1, then we get mg into L minus x is equal to ya k square into d theta by dx, or d theta is equal to mg into L minus x into dx divided by ya k square. If theta is the angle between the tangents at the points A and B as well, then we get theta to be equal to the summation of all such values which is being taken over one complete cycle, that is given by integration of, that is, mg into L minus x dx by ya k square. That is, summation means integration. Therefore, that is equal to, here we can take mgl by ya k square as common factor. Then we have to resolve this into two terms. One is mgl is one term, another term is minus mg into x. Therefore, we can write this as two terms as you are observing here. First term is mg into L by ya k square integration of dx, that is the first term, minus second term is mg by ya k square into x dx, integration of x dx, that is given by mgl by ya k square, integration of dx is x. The limits are 0 to L along one particular length, 0 to L dx. Integration of dx is x. Substituting the limits, we get L minus 0, upper limit minus lower limit. Upper limit is L, lower limit is 0. L minus 0, that is equal to L itself. Then L into L is L square. Therefore, that is equal to mgL square by YAK square. This is the first term, minus second term mg by YAK square into integration of x dx is x square by 2. Limits are 0 to L. So in place of x we have to replace by L, that is given by L square by 2. Therefore it can be written as mgL square by 2YAK square, that is the second term. So deflection of the cantilever is given by mgL square divided by YAK square, which happens to be the deflection of the cantilever. If dy is the depression of the beam, that is at the point B due to the curvature P dash, which is again represented back to the figure, then dy is the depression, that is equal to L minus x into d theta. Depression that is being produced beyond the point P, that is given by this dy, that is equal to L minus x into d theta, or d theta is equal to dy by L minus x. Substituting the equation 5 in 3, we get dy is equal to mg into L minus x whole square into dx by YAK square. The depression y is given by y is equal to, that is integrating on both sides. Integration of dy is y and integration of mg into L minus x square dx by YAK square. Here we can take mg by YAK square constant and integration of L minus x whole square into dx. This we have to expand as onto the lines of a minus b whole square, like that of a square minus 2ab plus b square, that is given by L square. First term is L square minus 2ab, 2L into x plus b square is x square. Now on integrating we get first term L square, integration of dx is x. So first term happens to be L square into x minus second term is 2Lx, that is 2L into integration of x dx is x square by 2 minus plus the third term is x square. Integration of x square is x cube by 3. The limits are 0 to L. That is given by mg by YAK square into L square into the limits are 0 to L. L minus 0 is L. So L square into L is L cube minus 2L into L square by 2. That is equal to 2L cube by 2. 2 cancels. We get that as L cube plus the last term is L cube by 3. Then on simplification, deflection, the depression of the cantilever is given by mg L cube divided by 3YAK square. For rectangular cross section, if B is the breadth and D is the thickness of the beam, then IG becomes, IG is equal to BD cube by 12. Then substituting this value of IG in the expression, we get the depression produced at the free end for rectangular cross section is given by y is equal to 4mgL cube divided by YBD cube. Then if this happens to be a circular cross section, if R is the radius of circular cross section, then IG is equal to pi R to the power of 4 by 4. Substituting the value of IG in the above expression, the depression produced is given by y is equal to 4mgL cube divided by 3 pi y R to the power of 4. This happens to be an expression for circular cross section. Thank you.